Hi guys, and welcome to our YouTube video course. In our YouTube video course, we will see how we can declare, define, and use C function in embedded system programming. First of all, we'll need to install and set up a set of tools to allow building and compiling our STM32 based project. We'll cover in terms of slides how we can declare, define, and invoke a C function within our embedded project. We'll cover as well the meaning of C function signature and how we can pass the input arguments and parameters to our C function, whether by value or by pointer. And we'll focus on the major differences between passing those input parameters by value or by pointer. We'll cover as well the keyword, qualifier, static, and inline, and their impact on the final assembly code generated out of our C program. And finally, we'll use our STM32 based project to execute a set of examples to demonstrate what we have learned across the different slides. We'll see how those C function that has been declared and defined within our examples will be executed within the STM32 microcontroller. And we'll see as well the impact of using the static and inline keywords type qualifier of our C functions on the final generated assembly code. So welcome to our YouTube video course. So beside the different slides which will explain how to declare and define a C functions, we'll have a set of examples that will be compiled, loaded, and executed by our STM32 microcontroller. Hence, we'll have an embedded project that will be used to compile those examples and communicate with our STM32 microcontroller. The hardware that I will be using to demonstrate and execute those examples will be an STM32L4 Nucleo board. The different tools needed to build the project, load it, and execute the program within our microcontroller will be located within this GitHub repository. The project source code, including the different C files, headers, and make files, will be located as well within our Wadix technology GitHub repository, and this is the link. And finally, the link to the different slides will be provided within our YouTube video description. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix tools GitHub repository offer quite big number in terms of toolings and applications. Nevertheless, for our makefile based project, we will need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU Make Build tool. And finally, we'll need set of tools and applications to be used in combination with our make file. So those applications will be used as part of our makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. STM32 does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our STM32 applications as well as make build tool as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now if we inspect again, as you can see, the previously added tools has been removed. Now I will just execute again this install PowerShell to be able to move forward within our makefile based project. As you can see, this has been added again. Now we can move forward and check out our makefile based project. Now, when it comes to the function declaration, definition, and invocation or call, we'll need first of all to distinguish between the meaning of function, declaration, definition, and call. A function declaration consists of creating the C function prototype that will be used within our embedded C program. This prototype consists of specifying the return type of the result coming out of our C function, then specifying and assigning a name to our C function. So this will be our function name, and finally listing the different input arguments and parameters to our C function. So this will be our C function prototype. In general, the function declaration will be done within a C header file. After creating the C function prototype, we will need to implement the body of this function. This is what is called a function definition. So here we will need to invoke the function prototype, similar to what we have done during the function declaration. So the return type, the function name, and the list of the input arguments. However, what we are going to add on top of the declaration will be the actual implementation of the body of the function. Finally, after declaring and defining our C function, we can invoke it within our program. The invocation consists of calling the C function name with a list of the input parameters to be passed to this function. Trying to invoke or calling a function that has not been declared previously will cause the compiler to throw a compilation error. Trying the invocation of a C function that has been declared but not defined will cause this time the linker to throw the error of undefined reference. Now, this is the example of how we can declare a basic C function within our program. This C function prototype, this is what is called a function signature. So the C function signature consists of the return type, the name of our function, as well as the different parameter type provided as input to our C function. All of those will be mapped or defining, let's say, the function signature. The C function definition consists of implementing the body of the previously declared C function. So here we need first of all to provide a matching C function prototype or signature to the declaration prototype. Means if we have declared this function within a header file, then the prototype of this declaration must be matching the prototype or the signature of the C function during the definition or body implementation. If we have a mismatch between the signature of our C function, between the declaration prototype and the definition prototype, then the compiler will throw an error. And then we can just implement the actual body of our C function. So simply, the function definition is just writing the body of our C function. In general, the function definition is done within a .c file. However, for some use cases, we can just implement the body of a function within a C header file. The different input arguments or parameters to be provided to our C function can be passed either by value or pointer. If the input parameters to be passed by value, then the variables which will be used to pass those parameters from the main program to our C function will be copied to the local context of our C function. This means that those variables, each one of those, will have its own memory location within our main program. However, when invoking our C function and then passing those input parameters to this C function, then we need to copy the content of those variables to the local context of this C function. Here, the local context can be basic processor registers, so those values will go to some internal processor registers. Then the C function will just get those values out of the processor registers. This, of course, depends from the C calling convention supported by our processor architecture. In some cases, those input parameters or variables will be passed to the local stack of our C function. Hence, we need to reserve two locations within our stack to hold the values of those input parameters. This means we'll have more stack consumptions for this use case. For the second use case, which is passing by pointer, here we are referencing the actual input parameters or variables provided to our C function. So we are not going to make a local copy of those input variables or parameters within our C function context. Actually, the C function, to load those values, will just access the addresses of the different input variables or parameters. So there is no need to copy those values to the local stack of our C function or making kind of local copy within the internal processor registers. We need just to keep a track of the memory addresses of those input variables or parameters. This, of course, will help us to save space within the local stack of the C function. So generally speaking, this will consume less stack compared to this use case, of course, in case those input parameters will be copied over to the local stack of the C function. However, if we're gonna use the internal registers of the processor to hold those input variables or parameters value, then the stack consumptions will be almost the same between the two use cases. And here we'll add extra complexity to keep track of the original memory location of those input variables. Hence, having this passing by value will make more sense. So really it depends from the use case of your C function and program. So if it is basic C function, so generally speaking, it makes sense actually to use passing by value for the different input parameters. However, if our C function is quite complex and will accept quite big number of input parameters, then it makes sense to pass them by pointer to preserve our stack consumption. For our declared and defined C function, we can label this C function with the keyword static. In this case, this declared and defined static C function will have kind of internal linkage. Our declared and defined C function can be tagged and labeled with the static keyword. If a C function is referenced and labeled with this static keyword, then it will have kind of internal linking. This means this static C function can be called only within the same .c file. And this .c file will be referenced as a single translation unit. So the visibility of this static function will be only within the context of this translation unit. And hence, we cannot reference this static C function from other .c or translation unit within our program. This helps, of course, to hide the visibility of our static function from other translation unit or .c file. So we start speaking about kind of private function. The static function, generally speaking, is not declared as part of public header file. A public header file is a header file that will be used by the different .c files within our program. And because the public header is shared between the different .c files, hence declaring a static function within this public header will risk to expose our static function. And this is, of course, we don't want to have it, because the main goal of the static C function is to reduce the visibility of this static function within the single translation unit or .c file. So hence, we'll need to declare our static function within a private header file that will be specific only to the translation unit that is calling and invoking this static function. Because our static function is limited to a single translation unit, this will enable the compiler to do further optimization within the context and the scope of this translation unit, compared to what if we are having this function shared between different translation units. There, in the second use case, will rely mostly on the linker or the linking stage to optimize further our program. However, with the static function, most of the optimization will be handled by the compiler within the scope of this translation unit that is referencing our static function. If by mistake we have invoked this static C function by another module outside the scope of this translation unit where we have defined our static function, then the linker at linking stage will throw undefined reference error. Finally, if you are defining a static function within a header file, then you are including that header file within different .c file. Each of those .c file will get its own copy of this static function. So you can think about it of having multiple translation units, and each of those translation units will have its own copy and definition of this static function. This is kind of redundancy, and it will increase the overall binary size. However, if we may think that this static function can be used across different modules and we need to keep it static to hide it from certain public users or program, then it's okay to define it within a single header file, and this header file will be shared only between the translation units that needs to invoke this static function. Inline function is just another type of C functions that allow the expansion of the body of the C function within the color program. This means during the invocation of inlined function within our color or calling, let's say, routine, the body of this inlined function will be expanded within the calling program itself. Hence, we will not have this standard jump back and forth between the calling routine and the called function. Actually, the body of the function itself will be expanded and will be part of our main function. So this is what is called inline function expansion. It is recommended in general to mark our C function as inline if they are small functions, as the impact into our binary size will be limited in comparison of doing the expansion of big functions. There, the impact will be huge, especially if we are planning to invoke this inlined function in many locations within our program. Hence, doing the expansion of a big inlined function within many invocation locations will lead to a significant binary size increase. So always the recommendation is to use the inline keyword for a tiny C helper function. Now, the standard practice of using static and inline keywords or labels with C functions is to use them both in the same time and having the C function, declare it, and define it within a single header file. So here we declare and we define the body of our static inline function within this header file. Then we can safely invoke and call this static inline function within our main C program. And of course, don't forget to include the header file that is declaring and defining the body of our static inline function. Now, the main question that you may have in mind is that why we will need to have both static and inline keywords labeling our C function, which is declared and defined within our C header file. The answer to this question depends really from the version of the compiler you are using. Now, for older compiler version and style, like the one based on GNU C89 style, even if you are marking a function or C function with the keyword inline, and the compiler will expand the body of the function within the main program that is calling this inline function, there is still a risk or a chance that the compiler will keep outline copy of the body of the function within our translation unit object or binary file. This happens especially if we are referencing the address of this inline function somewhere within our C program. In such case, beside doing the expansion of the body of the inline function within our translation unit, it will keep what is called outline copy of this function body somewhere in this translation unit. Hence, if we are going to include this header file that is defining our inline function within multiple translation units, there is a high chance that this outlined copy of this inline function will exist in the same time within multiple translation units. And this behavior is like more specific to this version of compiler. So during the final linking stage, we may get the error of multiple definitions of the same function, simply because in each of those translation units, we'll have our inline function defined there because of this outline copy of the body of this inline function, which does exist within each of those translation units. The solution will be adding this static keyword to our inline function. With the static, we are limiting the visibility of our inline function to the translation unit that is invoking this static inline function. So even if this header file is including or get included in multiple translation units, in each of those translation units, this outline copy of our function will have local visibility only within the context of a single translation unit. And hence, during the final linking, even if we have multiple versions of this inline function body within each of those translation units, but each of those has local visibility, and hence the final linking stage will not throw a multiple definition error simply because it doesn't see any of those outlined copy of the same functions, simply because the visibility is limited to the actual translation unit and is not external. Most of the compilers that exist in our day within the market are implementing the C standard C99 and C11. Now, if we pick up the same example as in the previous slide with the GNU 89 style, and we try to create an unlined C function within our C header file that will be called and invoked within a single translation unit, there is a chance, of course, that our translation unit, besides the invocation, may try to reference this unlined C function. Referencing means trying to invoke this function or getting the address of that function via invocation. So this is not a standard invocation or calling of a function where the unlined function will be expanded. No, here we are trying to get the address of the function and maybe get it to assign to a function pointer. In such case, we may fall into the same use case as the GNU 89 style. However, the behavior of the compiler will be different if we are in the C99 or C11 standard. Here, the compiler will not make an outline copy of the function within the translation unit. Actually, it will make it as external reference or external symbol dependency. So trying to reference this unlined function by address will lead to having a dependencies to an external symbol with the same name as our unlined function. So the compiler briefly will try to do certain optimization and avoid making outline copy of the unlined function within the binary of the translation unit. This will save us some code size. However, it will create an external dependency to an external symbol that has the same name of our unlined function. At least with this solution, we'll be able to compile our C source or our translation unit. But of course, this will create later on problems during the linking stage, simply because this external symbols is not defined in any other translation unit. Actually, is defined within our header file. And hence, the linker will fail and throw undefined reference error. The solution is to add this static keyword. If we add the static keyword to our unlined function, then the compiler will determine that this function visibility will be limited to the actual translation unit, and hence it will not issue an external symbol dependencies to the location where we are trying to reference our unlined function by address. In this case, it will enforce keeping outlined version of our unlined function within the translation unit, and hence will be able to resolve the dependencies to this unlined function, which is invoked by reference locally within the same translation unit. The cost, of course, is keeping outlined copy of this unlined function within the same translation unit, leading to an increase of overall code size binary. Now, this is our makefile based project, and this project is written to target an STM32 microcontroller. So the makefile project will consist of set of makefile roles that are needed to compile the different sources, generate the different object files out of those sources, and finally link those object files to generate the final ELF binary, and this binary will be loaded and executed by our STM32 microcontroller. The linker file is adapted for our STM32 microcontroller. Those are the set of sources needed to boot our STM32 microcontroller, and those are the set of headers needed by our examples and project. This is a predefined Kyle project needed to load our binary into the microcontroller and start a debug session within our STM32 microcontroller. And finally, those are the examples to demonstrate the different concepts and examples that we have seen across the different slides. So we'll start by a basic declaration and definition of a C function and how this will be executed by our microcontroller, and we'll be ending by a more sophisticated use case where we will see the impact of static inline on our C function. Now the first example consists of declaring and defining a basic C function that will be executed by our microcontroller. As you know, we'll need first of all to declare and create our C function prototype. This is to be done within a dedicated header file, as you can see. Now the signature and the prototype of our C function consists of the return type, and in this case it is an unsigned integer with size 32 bits. We're going to assign a name to our C function. This is add or addition. And finally, we need to specify the list of the input arguments and parameters. We must specify the type of each of those input parameters. So here we'll have two input arguments, each one of type integer, and that's it. Now the body of the function will be defined separately within a dedicated C file. During the definition of our C function, the prototype here must be matching what has been declared within our header file. If there is a mismatch, then the compiler will throw an error. And this is the body implementation of our C function. So this is the basic addition between the two input parameters, and the result here will be returned by our C function. And finally, our example will try to invoke this defined C function. Now to compile the project for our example number 0, we can just refer to the README to get the command to compile the project. So first of all, we need to clean the project. Now to compile it, we'll need to specify the example number to be compiled here. And we are through. A build directory will be created, and this one will contain the binary that will be loaded into our target device, the map file, and the disassembly, which is the set of the instructions opcodes that will be executed by our processor, as you can see. And this is the Kyle project that will be used to load this binary into the STM32 device, and of course will be used to execute and debug the program. Let's take a look into the disassembly file generated out of our example. The disassembly file will contain a representation of the different instruction sets to be executed by our processor. To have kind of one-to-one mapping between the C code of our example and the assembly representation of the example, it is better to turn off any high-level optimization level. High-level optimizations like O2, OS, OZ, and so on. So the default, if nothing is enabled, will be O0. And this will preserve kind of one-to-one mapping between the C code and the assembly representation of this C code. Now, this is our example. And here we are jumping to our defined C function add. Now the function here is defined and declared specially to accept input arguments per value and not per pointer. And on ARM Cortex-M calling convention, we'll have a set of registers which are called scratch registers like R0, R1, R2, and R3 to hold the value of the input parameters. If we are going above 3 or 4 input parameters, then the calling convention will use the stack to hold the value of those input parameters. Right now, our C function will accept only 2 input parameters. Hence, and based on this C calling convention for ARM Cortex-M microprocessors, the first one will be saved within the R0 register, and the second input parameter will go to the R1 register. Now, if we check the disassembly, we can see obviously that before jumping and branching to our C function, the R0 register and R1 register get initialized by the value of the input parameters to be passed to our function. So this is our function, as you can see, and those are the input parameters. So 10 should go to the R0 register, and this is what is happening, as you can see. And 20, because it is the second input parameter, will go to the R1 register. So now the add C function will be able to get the 2 input parameters out of those registers. This is our defined C function, and this is the assembly implementation of our C function. Here we'll see set of instructions will be used in general to get the input parameters do some arithmetic operations, because this is a basic addition between the two input parameters, and returning the result. And finally, we'll branch out of the function to go back to the main program here. So once we execute this branch with exchange to the link register, we'll be able to jump out from this function and go back to the main program. Now those calling convention and which instruction will do what exactly, I have a dedicated courses that can cover basically those aspects, and feel free basically to check those courses within our Wadex Technologies website, of course. Now back to our example. So those C functions by the end of the day will be translated to just basic set of instruction sets to be executed by our processor. And the way the main program will jump back and forth to the C function will be defined by the C calling convention to specify how the input parameters will be passed and prepared to our C function. If there are few input parameters, we can just save them within the internal registers of the processor. If there are many let's say input parameters, then most likely we're gonna use the stack to hold the value of those input parameters, and the function will be able to extract those input parameters out of the stack. Now, to be able to load our binary example into the microcontroller, we'll need first of all to start this Kyle project. This Kyle project will have the necessary configuration to load the binary into our STM32 microcontroller. Now, after loading, we can trigger a debug session, and here we'll be able to debug the binary executed within our STM32 microcontroller. Now, if we check out the assembly code here, we can see obviously that before jumping to our function, we'll need to prepare the input arguments and parameters context that will be passed as input arguments to the C function. Our C function does accept two input arguments, as you can see, and those two will be actually allocated as part of the CPU registers. This means the R0 and R1 register will be used to hold the value and the content of our input arguments to be passed to the C function. So this first parameter, which is 10, will be passed to the R0 register, and this value 20 will be saved within the R1 register. And actually the choice of having those two registers to hold the input arguments is defined within the C calling convention of ARM Cortex-M architecture. Now, once we have saved those values within those two registers, we can branch to our C function. Now here, within this C function, we'll need to execute this first routine to save some register within the stack, and those registers will be used within the body of the function itself. Now, as you can see, this R7 register will hold or will reflect the value of the stack pointer, So this is the value of the R7 register, and this is the value of our stack pointer. And here we are saving the first input argument and the second input argument of our function into the stack. And we'll continue the execution until we reach the end of our function to return to the main routine. And here we go. So here we'll restore the value or the initial value of our R7 register, and then we'll branch with exchange to our link register. So the link register will contain the address to where we should jump out of our C function to be able to return properly to our calling function or example. And here we go. We are back basically to our example. So the C function, by the end of the day, will be translated to a set of instructions to be executed by our processor. And the input parameters, in general, will be allocated and saved within the processor registers. And we'll have a predefined C calling convention to define the way to jump to our C function, then return properly from this jump. Now, in our second example, we'll see how to pass the different input arguments to our C function per pointer and not per value. In the previous example, we have seen how to pass the different input arguments to our C function per value. However, in the second one, those input arguments will be passed per address or per pointer. The major difference will be that here we had to save a copy of those values within some CPU internal registers, and our C function was able to get those values right away out of the CPU registers. However, here those values are saved in some memory addresses, and here we are passing those memory addresses as input arguments to our C function. So the C function will be able to access implicitly those input values by accessing the addresses of those variables. Here we may need extra assembly code to handle basically the addresses of those variables and how this function will be able to access those values via those variable addresses. However, the major benefits of such pointer users as input arguments or parameters to our C function is that we don't need basically to allocate that much stack for those input values or parameters. The major challenge with this first approach, which is passing parameters per value, if we are going to pass big number of parameters to our C function. In such case, the compiler will try to save some of those input parameters within the stack. And this will increase, of course, the stack consumption of our function or routine. However, in this case, we will not have extra stack, let's say, allocation, simply because the C function will just use directly the address of those variables to access those input parameters or values. Now let's try to clean up our project then build it again. This is our Kyle project. We load the binary, start debug session, and we'll jump right away to our example. Now, by inspecting the assembly code, we can see here that those two variables will be allocated within the internal stack of our processor. So this value here will be saved or passed to this R3 register, and the value of the R3 will be saved within this R7 register content, and this R7 actually is holding the value of the stack pointer. So those are just standard local variables that will be allocated within the stack. If we want those variables to be allocated globally within our data section or BSS section to reduce the stack consumption, then we need to move them here to be defined globally. Now, if we go back to our routine, we can see obviously that the R0 and R1 register will hold basically the addresses of the stack that are containing those two values. So this R2 is containing basically the value within the R7 register, and the value of the R7 register is the same as our top of the stack pointer. And this R7 offset by 4 will be basically the location of our second parameter. If we are jumping to our C function, we can see obviously that we are trying to save the content of the R0 and R1, and those one containing basically the addresses of those two local variables. And after that, we will try to load the different addresses out of the stack. So here we load it here to R3. Then out of R3, we loaded basically the value 10. So R2 will contain 10, as you can see. Then here we loaded again the pointer, and then we loaded the content of the pointer. So R3 will contain our second value. So as you can see, we had to add extra assembly routine to properly manipulate basically the accesses to the different pointers. And finally, basically we'll execute our program, and we are out basically of our C function. And the result should be 20. So hexadecimal is 0x14. Now with our third example, we're gonna see the impact and the influence of using this static keyword with our C function, especially when it comes to the C function visibility. So here I have marked my C function with this static keyword. So this C function will be restricted in terms of visibility to the current translation unit. So trying to import the C function from another translation unit will fail, of course, because the visibility of the C function will be limited to this current translation unit due to this static keyword. Now, one trick to see the impact of the static keyword at symbol level is just to try to inspect basically the labeling in terms of section naming of this function within our assembly, map, or even symbol file. Now, in practice, here we're gonna try now to build our second example or third example, let's say. Now, out of this compilation, we'll have set of file will be generated. I will be more focusing on this .symbols file. This one is generated by our build system, and to be more precise, it is generated thanks to this NM tool. So the NM tool will allow us to export the different symbols out of our .elf image, and also will expose the different identifier allocated and assigned to our functions and objects supported by our program. In practice, this means this file will contain the different function names, global variables that are defined and declared within our program. Now, in terms of identifier, we can see basically those symbols. So T here is standing for text. Now, if we inspect our add function, we can see that this T is a small one, not capital. A small one means the visibility of this function is local. So it will be limited and restricted to the current translation unit. So trying, for example, to import and use this C function from another C file outside the scope of our example will lead to an error, simply because during the linking stage, the linker will ignore the limited visibility of those functions. So it cannot simply see those functions during the linking stage, and this result of undefined reference or symbol. Why the visibility of this function is restricted to the current translation unit? Simply because we marked this function with the static keyword. Now, if I try to move the static keyword, then recompile the project, here we go. So here we are not talking about small t. Here we are having capital T. Capital T means the visibility of the symbol is not restricted or limited to the current translation unit. And hence, we can import and use this function from another C files or another translation units. With our third example, we have declared and defined a static align function. This static align function is declared and defined in the same time within a header file. Then this header file get included to the main .c file, and we make use of this inline function, as you can see. So first of all, we have created a reference to the location of this C function or align C function, and then we made a normal invocation and call of this align C function. Here we'll try to observe the impact of this align keyword and how it will allow just aligning and exposing, let's say, the body of the function as it is within our example. So we'll not see a branch with link to the C function. Actually, the assembly content of the C function itself will be exposed and expanded within this example as it is. And here, for this reference to the address or the location of our unlined C function, we'll try to use this to highlight the impact of the outlining of our unlined C function. So this one will enforce our program basically to keep a reference to the implementation of this C function. However, with most of the C99 based compilers, it will not keep an outlined or a whole implementation of the C function itself as it is within the current translation unit. So here it will try to resolve this at linking time. In another word, this will be kept. However, this one, it will be referred as external symbol, simply because the real implementation of this function will be removed. So the C function will not have a dedicated memory address. And the body of the function, whenever it is called, it is expanded. So our main program is not aware of the existence of such function. And to resolve or prevent any compilation error, then the compiler will try to refer this function as external symbol so that the linker can resolve it. However, during the final linking stage, and because this function itself is not allocated within our memory and it will not have a real reference, then the linker will fail and will throw an error of undefined reference. This is why we must add the static keyword. Static keyword will enforce, in this case, the compiler to identify this function as local one to the current translation unit. And hence, it will not try to resolve this reference to our function location by making it as external symbol. Actually, no. So it will outline this function. This means it will allocate some memory space for it, and it will keep it as a standard and normal C function. And hence, the translation unit itself will embed the reference of this unlined function, and it will try to resolve it within the current translation unit, even without reaching the linking stage. Here, of course, the function itself will be expanded, so we will not do any branching, but here we will need to keep a reference to this function so that we are able to resolve these dependencies or reference to it within the current translation unit. This may sound a little bit complicated from top level perspective. However, once we start to inspect the finally generated disassembly file, we'll see the impact of using static and inline keywords together to label our C function. So first of all, we'll need to clean up our project. Then we'll need to build our final example. Now, before we build it, I will try to remove the static keyword. Now, as you can see, once removed, I will get this error, undefined reference to add. This means simply is that this function here we're able to unline, but here for this line, because we have been referring to the location of our function, the compiler tried to resolve this by creating a fake reference to an external symbol that doesn't exist. With that, it was able at least to pass the compilation stage without problem. However, during the linking tried to find the reference to this function, but this one has been removed. The compiler didn't keep it while compiling basically this source file, simply because it expanded the body of this one here, and then it removed the whole function and no memory address has been allocated to it. So in the final linking stage, this failed right away. To solve this, we had to add this static keyword. We need to rebuild again from scratch because we have modified the header file and not the C file here. And I don't have, let's say, dependencies to any modified header file. So it means modifying the header file will not trigger, let's say, build flow dependencies to generate from scratch the elf and the disassembly. So I need to clean up everything and rebuild everything from scratch. However, you can update the build system later on to create dependencies to any modified header file. Anyhow, back to the main topic. Now, as you can see, the build flow has been done properly with success. And if we inspect the disassembly file, as you can see, we have allocated some memory area to our C function add. So this one will have a dedicated memory address. Having a dedicated memory address allocated to our C function means we can have a reference to this one, and of course we can use it as normal function per address. So we can refer the address of the function, and we can create as well a function pointer out of the C function. And this was possible only because we have added this static keyword. So the compiler is forced to solve this reference to the address of our function within the current translation unit. So he had to create and reserve a memory space for the function, and he had to keep the implementation of the C function, and then here we were able basically to refer it properly, and we were able to link properly as well. Another important point to highlight here is that if we don't enable the auto optimization at least with our compiler, then this inline keyword in most of the cases will not have any impact, and the normal branch with link to our C function will be kept. Here in our case, we can see obviously that we are branching with linking to our inline C function. So the inline C function was not expanded here. This means that the inline keyword didn't have any impact. And if we inspect the compiler flags, we can see obviously that this auto optimization level was not enabled. Now, if we recompile our project with the auto optimization level enabled, we'll see that our inline function has been expanded. So we don't see this branch with link to the inline C function. What we see is that the body of the function itself has been expanded as instruction set within our calling routine. And this is basically the implementation of our unlined C function. With this, we're able to see the impact of this unlined keyword. Let's say the recommendation here is to use the unline keyword with a function that they don't have, let's say, big implementation. This is to keep the increase in terms of code size under control. If we try to enforce the unlining of big functions, then we'll have big impact in terms of code size added to our final binary size. And this outlined implementation of our unlined C function is due to the fact that we try to reference the address of this unlined C function. Hence, we will need to keep basically a memory space allocated to the implementation of our unlined C function. Without this, then we will see the previously demonstrated error with undefined reference.